Okay, so in today's lesson, I apologize. We lost you if you were at home, so I'm going to try to repeat that lesson here very quickly. Okay, so we'll cover some of the key aspects of what we did in class today. Actually, I'm going to just pause and pick up another couple of markers. Okay, so where we had started class today was looking quickly at where we had ended yesterday. Okay, so if I had two vectors, A cross B, we had shown yesterday that if C was this vector cross product, okay, then C dot A was 0 and C dot B was 0. Now we want to figure out why that is the case, okay? So these mean things, right? C dot A equals 0 means that C is that showing up very well? Let me switch colors here. Let's stick with black and blue. This means that C is perpendicular, that's what that means, to A. This also means that C is perpendicular to B. So both of those things are true, all right? Now, C is perpendicular to A and to B. What is the meaning of that? Well, we determined that this means that A and B form a plane. Okay, and when you put these two things together, this means that C is perpendicular to the plane. So we're going to later on say, well, that means it is perpendicular is normal to the plane. And in class tomorrow, we'll talk about this, meaning that C is the normal vector to the plane. Okay, well now let's talk about why that would be the case. Okay, so let's say that A and B are two vectors that form a plane, and let's use the blue marker as A and the black marker as B. Right? We learned yesterday that when you have to rotate the first vector into the second, all right, to get the direction of the cross product. So the cross product does have a direction, and if you rotate the blue into the black, and you're using your right hand, your thumb points out of the board. Okay, if you were doing this one, if we put the board on the ground, and it was like your piece of paper on your desk, it'd be pointing out of the page towards the ceiling. But since we're using the blackboard, it'd be towards the back of the room. Right? That would be true even if A and B are not perpendicular to each other. That A cross B would still be towards the back of the room, which would be perpendicular to the board. So if A and B are in the plane of the board, C will be perpendicular to that. Okay. Now, if I put A down here, okay, so A cross B rotates the other way, then my thumb, as I rotate A into B, my thumb will point into the board, okay, which is still perpendicular to the plane of the board. So the resulting answer is either out of the plane or into the plane, but it is perpendicular to the plane either way. All right? Now, the same thing would be true if these were on the level of the floor. Let me just tilt them up a little bit. The blue marker is now going to be pointing into the board, and the black marker towards the wall over there. If I rotate blue into black, my thumb points into the ceiling. Right? Whereas if I switch where the blue marker is, so that it's in the front, okay, I'm going to rotate it up. Blue rotated into black would be pointing down towards the floor. Okay, so if the blue and black markers are in a plane that's parallel to the floor, then the resultant is up. The cross product will have a direction which is up or down, depending on the order in which the vectors are applied, which one is being rotated into which one. Okay. So we saw that all of that would be true, okay, and so we can determine a vector normal to a plane by taking the cross product of two vectors that are in a plane. Any two vectors will form a plane. And let me go over why that would be the case. Okay? So let me, actually here's a nice little flat plane. Okay, it's a little mini whiteboard, all right? If I have one vector, it's along a line. Okay? And if I look at that, I could have a plane that contains that line, but there are an infinite number of planes that contain that line. Okay, now they're similar to, they all are, if they contain that line, they're rotations of one another along that line. Okay, but any one of these rotations will still contain the line, back on this side, the line that I have. Okay, so I can rotate along the line. If it's a diagonal line, I might be rotating like this. There are an infinite number of planes that all contain one vector. Okay, but if I take two vectors, okay, and I place them like this, there's only one plane. Turn this way. There's only one plane that can contain both of those. All right. So each of those vectors has an infinite number of planes it could pass through, but only one of those planes, okay, will contain both vectors. Right? And remember, planes extend forever like lines do, so it doesn't really matter if it's here or here. It's going to go outward forever. So no matter where I put my two vectors, there will only be one plane that can contain both of those vectors. Right? So as soon as I'm given an A and a B, I have defined a plane that I have. Certainly, I haven't necessarily given a point on the plane, but I've defined a direction of the plane. Okay, so it determines the angle of the plane in the X, Y, and Z directions. Okay, so that's what is happening there. So any two vectors define a plane, and their cross product will give me the normal to the plane. Okay. Now, if we think of points instead of lines, okay, one point will not define a plane. Okay. If I have one point right here in space, and I put my plane on it, that's one plane. Here's another. There's another. All of these planes rotating in any which way. All there's an infinite number of these, but they're not contained at all. So there are lots of ways that we could put these planes. An infinite number of planes could be constructed that go through that one point. But if I create 2 points, let me do this over here. So 1 point does not define a plane, but 2 points defines a line. We already talked about that. Well, if you have a line, now it doesn't give you planes that could be any which way. They can be rotated around that line. So we have a smaller infinity of planes that could contain the 2 points instead of just one. All right. Now the third point would define a plane. Okay. So if I have a third point and I put it down here, okay, there is only one plane that contains P, Q, and R. Okay. Only one plane. I've drawn them in the plane of the board. But if I move R out here, it would be P, Q, and R like that, okay? I could move point, keep that there, and then move point Q out here, and any 3 points will define a plane. So this little triangle is a bit of area that's flat, okay? And right now it is the plane of the whiteboard, but we could rotate it in any which way. But once I put 3 points in space, I will have, it will define a plane, right? Now, continuing with that idea. All right, one thing does need to be true about R. If P, I used green there a moment ago, hopefully it shows up. If P, Q, and R are in a line, they are called collinear. They're on the same line. Then that doesn't define a plane. I have to bring the third point off of the line of the first 2 in order to define a plane. So now if R is here, I can define a plane. Okay, now if I have 3 points in a plane, I can use those points to get vectors. There would be the vector PQ. I could flip it and have QP. Here's a vector PR. I could flip it and have vector RP. And then there's a third vector, QR or RQ, that can be drawn in there. But we only need two of them in order to define the plane. Okay? So let's look at a few points. Let's say that P is the point 2, 0, 3. Q is the point 0, 1, 2, and R is the point 1, -1, 2. Okay. Now there's one thing I want to point out here. You'll notice that P has 0 in the y direction. If it has 0 in the y direction, if I just black, move the green out here so I don't accidentally use those. If I have 0 in the y direction, and I draw the x, y, and z axis like this, if I have 0 in the y direction, it means I'm on the xz plane. Okay? So in this picture of the corner of the room, it would be sort of the left-hand wall would be the xz plane. So point P is over here on the xz plane. Point Q, it's missing the x. So that means it's on the yz plane. In this picture, that's the back wall. Okay, so the yz plane is back over here. Okay, now this point has all 3 coordinates, so it's out in the space. It's not on any one of the planes. Okay, so there's an xy plane that would kind of be like the floor. Okay, there's a xz plane, which is kind of the wall to the left, and the yz plane, which is the front wall of the room. And if you tilt everything, then you have the floor, the left wall, and the right wall, depending on how you're looking at the corner. So if you're looking at the corner head on, you have the left wall, the right wall, make that darker, and you would have the floor down there. Okay? So, just a little side. So when you see zeros, it's telling you something. All right? In fact, let me do one more point. If I have the point S, that was 0, 0, 4, 5. Okay, this has no x value, no y value, but it does have the z value. This is on the z axis. All right? So it's not on one of the planes, it's right on the z axis because there's no x and no y value. Continuing on. If I have these points, I can create vectors. Let's make a vector PQ, and then I'll make a vector PR. So vector PQ, we put a vector symbol on that, and vector PR. To get from P to Q, I have to go down 2 in the x direction. From 2 to 0, I went down 2. To get from 0 to 1, I better go up 1 in the y direction. To get from 3 to 2, I better go down 1 in the z direction. To get from P to R, I had to go down 1 in the x direction, 2 minus 1. To get from, I'm sorry, I need to go 1 minus 2. I have to go down 1. And then to get from 0 to -1, I go down 1. That's -1 minus 0. And to get from 3 to 2, I also have to go down 1. So that's -1, -1, -1. Right? Now, let us do the cross product. And so these two vectors define the plane. I can find the normal to the plane. N will be P. Let me actually write this over here. Create a little more space. Actually, I'll write this down here. N is equal to PQ cross PR. Okay, that will give me a vector normal to the plane. So how do I find N? We just do what we did yesterday. Okay, we set up I, J, K, and PQ is -2, 1, -1. PR, -1, -1, -1. we're taking a determinant, but we're thinking of this wrapping around. Okay, -2, 1, -1, -1, -1, -1. So the forward diagonals will give me the positive contributions, and the backward diagonals will give me the negative contributions. So first diagonal, we have a -1i. I could just call it -i. Second diagonal, +1j. Third diagonal, that would be +2k. Then I'm going to subtract. I'm going to take this vector, and I'm going to subtract it as a unit vector form, so I can actually use parentheses, and I'm going to subtract the backward diagonals. So I'm going to subtract, that's -1 times -1, I'm going to subtract I. Okay, and then -1 times -2 is 2, so I'm going to subtract 2j. And then I will subtract -1k. So here's line them up like this, it's easy to do the subtraction. -i minus I is -2i. J minus 2j is -j. 2k minus -k becomes +3k. All right, so the vector n can be written in unit vector notation as 2i minus j plus 3k, or in component form as -2, -1, 3. So vector n can be written either of those two ways. Okay, now it's pretty easy to show that n is perpendicular to PQ and QR. Let me just show that n dot PQ is 0. Okay, this is a good way to check that I did the work correctly. So let's do -2, -1, 3, dotted into -2, 1, -1. So the first term of the dot product is 4, -2 times -2. Then I get -1 times 1, so that's -1. And then 3 times -1 is -3. And I can see that does give me 0. So it's a good way to check that I did the work correct. This is a bit time consuming to find the cross product. So you don't want to do it again to see if you are right. What you want to do is take your answer and dot it into one of the vectors in the plane. And if you get 0, you probably did it correctly. If you get 0 when you do it, dot product with both vectors, you know you were right. Okay? But this is just a quick check to take the dot product with one vector. Right? So that's like a normal vector to a plane. Right? Now, we want to get into the cross product theorem. Okay, we have the dot product theorem already. This is similar to the dot product theorem. Okay. Here are the differences. Okay, we want this to be maximized when things are perpendicular. So the sine is maximized at 90 degrees. Okay, the cosine is maximized when things are parallel. So the cross product theorem has a sign in favor. Another difference is because A cross B is a vector, we need to make it into a number by taking the absolute value sign. Putting the absolute value sign around that is the magnitude of the vector A cross B. All right. Now let's apply this to a couple of things. Let's first of all apply this to what I said the other day about torque. Okay, torque was R cross F. This means if I want to find the amount of torque, I can take the size of R times the size of F times the sine of the angle between R and F. Okay, so let's have a lever arm. Let's say my bolt is right there and I have a lever arm out to here, which is 2 feet long. And then let's apply a force on the handle here. in this direction, that's 120 degrees, okay? And we'll make the force equal to 10 pounds. So we have a 10-pound force at 120 degrees from the end of the lever. All right? Now here's a good question. Okay, I could redraw this. And we'll talk about why we might want to do this. Just a moment, I can put the 10 pounds up there, and then this is a 60-degree angle. So it's clear, if I want to find the magnitude of the torque, I'm going to take R times F, the magnitude of R times the magnitude of that. So the magnitude of the torque is 2 times 10. And the part's clear, that's going to be 20. But then I have the sine of theta. The question is, do I use the 120 or the 60? And the answer is it doesn't matter. Okay? Because you hopefully remember, I'll draw this down here and then erase it. I have a unit circle. If I'm at 60 degrees, there's a specific sine value, turn it to be √3/2. But there is somewhere else on the circle that has the same y value. And that's this point over here. And you can see by the symmetry, this would be, if this is 60 degrees over here, this is 60 degrees back from 180, which is 120 degrees. So the sine of 120 and the sine of 180 are the same. The sine of supplementary angles, those that add up to 180, will be the same. So in physics, we don't really worry if we use the 60 or the 120. You can take any of these angles. This would obviously be 60 or 120 again. You can take any of the angles when you're trying to find the torque, okay? But if you want to find the direction of the torque, you need to line the vectors up tail to tail, like the hands on a clock. Because remember, to find the direction, you have to rotate the first vector into the second. So if I rotate R into F, this tells me if I rotate R into F, my thumb points out of the board. So this torque actually has a direction which is pointing directly out of the board. If I apply a different force, let's put this in black, at the end of this lever arm, I was going to say this way. Then when I put it tail to tail, it would be down here. If I rotate R into that F, R would rotate clockwise in the plane forward, and F would be down. So that torque would be into the board, would be the opposite direction. So you actually then could add the torques together. Actually, this torque would be out of the board, the torque from the first force, the torque from the second force would be into the board. So you would add their sum together, making out of the board positive, into the board negative. So you could combine them with multiple torques. Okay, it's pretty easy to add them up. Right. Now let's look at another example. Let's find the area. Let's use this theorem to calculate the area of a parallelogram. Okay, it turns out this formula works very nicely because let's say I have a side A. And my parallelogram connects to these points. And then there would be a couple of other points over here. Okay. The parallelogram would do that. So if I had points with P, Q, R, and S, okay, as corners of the parallelogram, we would see actually P, Q, and R, S are the same vector. We made those into vectors connecting those points. And P, R, and Q, S would also be the same vectors. If we wanted to add vector A and vector B, we know we can draw this diagonally, okay, to add them up. But now what I want to do is consider there's an angle theta between them. And I want to consider what does AB sine theta have to do with the area of this parallelogram. Well, you hopefully remember that for a parallelogram, you get the area by multiplying the base times the height. Well, to get the height of the parallelogram, I have to drop a line called the altitude. And how big is this line? The height of this is the hypotenuse times the sine of theta, because this line is opposite to the angle angle theta. So what is the area of the triangle, or I'm sorry, of the parallelogram? Area is A sine theta times B. This would be the height times the width, which we could rewrite as A B sine theta. Now, we were actually biased towards making B the base. We could have actually made A the base, and then we could drop an altitude this way, and the line I just drew, the altitude would have a height, draw it over here, of B times sine theta. So I could take base A times the altitude, which would be V sine theta. And you can see because multiplication is commutative, we get the same answer. So rather than worrying about which one is the altitude, which one is the base or not, we can simply take the magnitude of the two vectors representing the sides and take the sine of the angle between them and multiply those three factors together to determine the area. Okay. Now coming back over to the cross product theorem, right? We know that N is A cross B. Look at this with other vector names. We call this C, but we just talked about how this is the vector that is normal to the parallelogram. Okay, and so what we found, this area must be the same, okay, as the magnitude of N. Okay. So if we were to cross A and B, we would get a normal vector that is into the board, and it would have a magnitude, and the magnitude of that normal vector would in fact be the area. So the magnitude of N is equal to the magnitude of A cross B, and we just found that that is AB sine theta, so we just found the area using AB sine theta, and that is the same as the magnitude of the cross product or the side of the normal vector to the plane if we do A cross B. Okay, so if I gave you two vectors in component form, let's say I gave you that A was a vector that was 2, 1, -1, and B was, let's go with -1, 0, 2. I could find the area of the parallelogram by saying, I'm not going to work through this now. We've done enough cross products now. The normal would be A cross B. And then I could take the magnitude of that normal vector, and it would be the magnitude of A cross B. And let me just remind you, this is a 3D Pythagorean theorem. So if I wanted to get the size of the normal would have been broken down into an X component, a Y component, and a Z component. And we can say that the magnitude of the normal is, using the Pythagorean theorem, the square root of the sum of the squares. Okay, so once we figured out how large the normal vector is, we could use that in order to determine what the area of the parallelogram is that has these two vectors of size. And there we started talking about trying to derive the equation of a line in 3 dimensions, but we'll be in class for that tomorrow, so you'll see enough of that tomorrow.